All right, let's dive right into one of the coolest concepts in all of physics, projectile motion. But forget dusty textbooks. Today, we're going to look at it as a tale of two worlds.
You know that perfect arc a ball makes when you throw it? It looks so complex, so elegant. How in the world does a simple object trace that exact path every single time? What's going on there?
Well, the secret is actually kind of mind-blowing in its simplicity. It's like a magic trick. The projectile isn't following one super complicated rule. Nope, it's following two incredibly simple rules at the exact same time. It's literally living in two different worlds, and once you get that, everything clicks into place.
So, let's start unpacking this whole tale of two worlds thing. But first, we gotta lay down some groundwork. What even is a projectile, and what are the rules of the game? Okay, so projectile is just the physics speak for any object that's been given an initial push and is now just flying. Think of a cricket ball after it's been hit, or a javelin after it leaves an athlete's hand. The key, and this is super important, is that once it's flying, the only thing we're paying attention to is gravity pulling it down.
Now, to keep things clean and simple, physicists set up some rules for this game. We pretend gravity is just a constant 9.8 meters per second squared, always pulling straight down. And this is a big one. We completely ignore air resistance. So in our perfect little physics world, there's no wind, no drag, nothing to mess with our projectile. These assumptions let us see what's really going on.
And here it is. This is the big reveal, the secret sauce. Every projectile's motion is actually two separate stories happening at once. You've got the horizontal world where it's just gliding along. No forces, no acceleration, just smooth sailing. And then you have the vertical world, where gravity is the star of the show, constantly pulling down, always changing things. These two worlds exist at the same time, but get this, they never, ever interfere with each other.
So, let's take a trip to that first world. The horizontal world is, honestly, kind of boring, but in a good way. Imagine you're in a car on a perfectly straight, endless highway with the cruise control locked in. That's it. That's the entire story of horizontal motion. So the horizontal velocity is just that sideways piece of the initial speed. And the most important thing to remember is, it never changes, ever. From the second it's launched to the second it lands, that sideways speed is constant. Because in our perfect physics world, there are no horizontal forces to slow it down or speed it up.
Okay, now for the second world. And this place is way more dramatic. The vertical world is a constant battleground. You've got the initial upward motion fighting against the relentless downward pull of gravity. It's a non-stop tug of war.
And this is where we find the vertical velocity, the part of the launch speed pointing up or down. Unlike its horizontal buddy, this velocity is always changing. Gravity is constantly yanking on it, so the object slows down on the way up, stops for a split second at the very top, and then speeds up all the way back down.
Right, theory is great, but let's see how this two worlds idea actually helps us solve a real problem. We're going to tackle a classic cliff problem, and you'll see just how easy it becomes when you treat the horizontal and vertical parts separately. This is where our two worlds finally come together to give us the answers.
So here's the scenario. We've got a ball. It's thrown perfectly sideways, horizontally, at 20 meters per second from the top of an 80-meter high cliff. We need to figure out two things. How long is it actually in the air? And how far from the base of the cliff does it land?
And our plan is super simple because we're using our two worlds thinking. Step one, we're only going to look at the vertical world. We'll ask it one question. Hey, how long does it take for something to fall 80 meters? That answer gives us the flight time. Step two, we take that time over to the horizontal world and use it to figure out how far the ball glided. Simple as that.
Okay, step one. Let's put on our vertical-only goggles. Right now, we honestly don't care that the ball's moving sideways. All we see is an object being dropped from 80 meters high with zero initial vertical speed. So we just plug those numbers into our standard equation of motion. You run the numbers, and boom, 4.04 seconds. That's how long the ball is in the air. This number is our golden ticket. It's the one piece of information that connects our two separate worlds. It's the key. Now for the easy part, we take our key, at 4.04 seconds, and we just stroll on over to the horizontal world. And remember, life is simple here. Distance just equals speed times time. We already know the horizontal speed has been a rock-solid 20 meters per second the entire time. And there you have it, 80.8 meters. The ball lands that far from the base of the cliff. See? By splitting a complex problem into two really simple ones, we found the answer. No sweat. That's the real power of thinking this way. So, you might be wondering, is this just a neat trick for homework problems? Absolutely not. This two worlds thinking isn't just a trick. It is the fundamental way physicists understand motion. Let's look at how this exact idea shows up in real exam questions.
Check this out. This concept from a NEET 2019 question is literally the definition of our horizontal world. No net force means no acceleration, which means velocity stays the same. That's Newton's first law, and it's the only rule you need for the horizontal story.
And this one, from a 2018 exam, is the principle itself. It's telling you flat out, to understand the big picture, you have to break it down. Analyze the x motion and the y motion as two separate puzzles. That's exactly what we just did with the cliff problem.
Here's another one. A concept from a 2007 paper shows how the two worlds combine to make that beautiful arc. Where the object is at any given time is just a combination of how far it's glided sideways and how far it's fallen down. The relationship between those two gives you its path.
Ah, and this is a classic, a total favorite. At the very tippy top of its flight, the object stops going up for just an instant before it starts coming down, so its vertical velocity is 0. But what's happening in the horizontal world? Nothing. The cruise control is still on. It's just gliding sideways, completely unaware of all the drama happening in the vertical world.
So that elegant arc isn't one complicated path. It's just two simple stories being told at the same time. A steady, boring, sideways glide, and a constant, dramatic downward fall. Once you see it that way, you can't unsee it. Every time you see something fly through the air, you're watching a tale of two worlds. So, what are you going to see differently now?